Two pipes. The same 10 meters, the same air and water, the same slug train fed at the same inlet, the same pressure drop. Both of these are the output of a working, mass-conserving solver. And they disagree completely about what the flow looks like. The top pipe is the first-order upwind scheme we built in Part 1. Its slugs are dissolving into fog, the fronts have smeared across 40 centimeters of pipe. The bottom pipe is the exact same equation, solved with a TVD limiter. Its fronts are 5 times sharper, and it cost us 6 extra lines of Python. Today, where that fog comes from, why the obvious fix makes things violently worse, and the 1980s idea that solved it so well that every serious CFD code on Earth still uses it. As always, derived first, coded second, verified third. First, let us catch the culprit red-handed. Why does upwind smear? Take the upwind update from Part 1 and tailor expand every term. The algebra is 3 lines, it is in the derivation PDF, and the result is damning. Upwind does not solve the advection equation. It solves an advection diffusion equation, with an artificial viscosity, U delta x over 2, times 1 minus the Courant number. We never asked for that diffusion term. The discretization smuggled it in. Put our numbers in. Velocity 1.2, cell size 25 mm, Courant 0.9. The fake viscosity is about 1.5 times 10 to the minus 3 meters squared per second. For scale, that is more than 1,000 times the molecular diffusivity you would physically expect here. Our slugs are swimming in numerical honey. And here is the measurement, straight from the solver, the final alpha profile along the pipe. Each front that entered as a perfect step now takes 401 mm to climb from 10 to 90% gas. 16 cells of fog, and it grows with every step the slug takes. The obvious diagnosis, upwind is only first-order accurate. So reach for a second-order scheme and the diffusion term vanishes from the Taylor expansion. Meet Wendroff. Second order in space and time. On paper, the smearing is gone. Let us run it on the identical slug train and look at the answer. The fronts are sharper, yes. But look at what surrounds them. Oscillations. The solution overshoots to alpha equals 1.18, a cell that is 118% gas. It undershoots to minus 0.18, negative gas, 18% of gas that does not exist. Feed that into a mixture density and your solver is now computing physics for imaginary fluid. And this is not bad luck. It is a theorem. Godunov proved in 1959 that no linear scheme of second order or higher can avoid creating new oscillations. Read that carefully, because it contains the escape route, the word linear. If we want sharp and clean, the scheme itself must become nonlinear. It must look at the solution and adapt. So we need a property, something measurable, that separates honest sharpness from oscillation. 1983, Ami Harton, total variation. Total variation is the sum of the jumps between every pair of neighboring cells, the total amount of up and down in the whole profile. A clean slug train has a fixed total variation, each front contributes exactly 1, however sharp it is. But every new wiggle, every overshoot, adds extra up and down. Oscillation is precisely the act of creating new total variation. So here is the demand we place on our scheme: the total variation must never increase. Total variation diminishing. TVD. A TVD scheme is allowed to smear a little, allowed to steepen, but it is structurally forbidden from ever inventing a new wiggle. And we can measure it, live, from our own solver. The coral curve is Wendroff. Its total variation climbs relentlessly as it manufactures wiggles. The teal curves are upwind in the Van Leer limited scheme we are about to build, bounded, forever, exactly as the theory promises. This plot is the whole episode in one picture. Here is the construction, and it is beautiful. Write the face flux as upwind, plus a correction toward Wendroff, and put a dial on the correction. The dial is the limiter, phi. Turn it to 0 and you are back at part 1's upwind. Turn it to 1 and you have lax Wendroff, wiggles included. The nonlinearity that Godunov demands enters through the dial's input, R, the ratio of the upstream slope to the local slope. Where the solution is smooth, R is near 1. At a sharp front or a wiggle, R swings wildly. The limiter reads R and decides, cell by cell, every time step, how much second-order correction is safe. Swebey mapped the safe territory in 1984. Any curve phi ever living inside a particular wedge is provably TVD. 3 residents matter today. Minmod, the cautious one, always takes the smallest safe correction, front width 200 mm, half of upwind's fog. Van Leer, the smooth diplomat, 150. And superbee, the aggressive one that leans on the wedge's ceiling and actively steepens fronts, 75 mm. 5 times sharper than part 1, with 0 oscillation, guaranteed by construction. Time to write it. 7 steps, and as always, every line on screen runs unmodified in the download. Step 1, the identical pipe, grid, velocity, and Courant number as part 1. Nothing about the physics changes today. Only the transport scheme. Step 2, and this is my favorite design decision in the whole file. Every scheme in this episode is one small function, the limiter phi. Upwind is the function that returns 0. Lax Wendroff returns 1. Minmod, Van Leer, and superbee are 1 line each. Swapping schemes is swapping a function handle. Step 3, ghost cells. 2 upstream cells carry the inlet value, because a second-order face needs 2 levels of upstream information. 1 downstream ghost copies the last cell, a 0 gradient outflow. This is the same conservation lesson as part 1, upgraded for a wider stencil. Step 4, slopes between every neighboring pair, then the smoothness ratio R, upstream slope over local slope, with a tiny epsilon guarding the division. 2 number py lines for the entire field. Step 5, the limited face value. Upwind value, plus the dialed fraction of the lax Wendroff correction. Multiply by U and these are the fluxes at all 401 faces. Step 6, the flux form update, and the reason we never worry about conservation again. Each cell changes only by flux differences, so whatever leaves one cell enters its neighbor, by construction, whatever the limiter does. Step 7, we do not trust that claim, we test it. The volume audit from part 1 runs for all 5 schemes. The worst offender misses by 2.8 times 10 to the minus 15. Round off. All 5 schemes, exactly conservative. The race you have been waiting for. Same inlet, same clock, 2 schemes, and every frame of both pipes is the solver's own alpha field. The brightness of each gold slice is literally the computed gas fraction, fog renders as fade. Watch the first slugs enter. For the opening meter they look similar. But the upwind fronts start bleeding immediately, and the damage compounds, every time step adds another layer of artificial diffusion. By mid-pipe the difference is brutal. The top slugs are ghosts of themselves, fading at both ends. The Van Leer slugs still have faces, you can point at where each one begins and ends. And at the outlet, the verdict. 400 mm of fog against 150, on identical physics and identical cost per cell, 6 extra lines of code. This is why no production CFD code transports interfaces with plain upwind. 3 claims were made today. TVD schemes do not oscillate. They are sharper than upwind. And they conserve mass exactly. A claim each deserves a check each. Check 1, oscillation, we already saw on the total variation plot, bounded for every limited scheme, growing only for unlimited lax Wendroff. Check 2, sharpness, quantified, upwind 401 mm, minmod 200, Van Leer 150, superbee 75. And check 3, in the last column, the conservation audit for all 5 schemes lands between 10 to the minus 15 and 10 to the minus 16. Flux form keeps its promise no matter which dial we install. One honest caveat before anyone marries superbee. Its aggressive steepening treats every profile like a front, so genuinely smooth waves slowly get squared off. For slug interfaces it is magnificent. As an everyday default, Leer is the balanced choice, and it is what this series uses from here on. Take stock. We caught upwind red-handed with a Taylor expansion and measured its fake viscosity. We watched second order create negative gas and met the theorem that says it always will. We demanded a property, total variation diminishing, built the limiter dial that enforces it, and raced the schemes in 3D fronts 5 times sharper. Conservation still at machine precision, for every scheme, because flux form makes it structural. Part 3 is in your hands. The pinned comment poll is still running. Drift flux slip between the phases, against pressure transients, water hammer with gas. Vote, and that is what we derive next. All 5 limiter solvers and the full derivation PDF, including the Taylor expansion from today, are in the flow from scratch pack linked below. If watching a theorem lose to 6 lines of Python is your kind of engineering, subscribe. See you in part 3.